A good way to study what electric field means is to look at gravity field. We are all on a planet that is spherical in shape, but it's so big that at any given point we think the gravitational field of being uniformly downward. But if you look at the entire Earth, it's not like that. In fact, the gravity field throughout the surface of the Earth points directly towards the center of the Earth. So that's something that you all know. And then if you go farther away from the Earth, like several miles from the Earth's surface, say a few hundred miles, we know that the gravitational force is going to be weak. And then if you keep going out to infinity, the gravitational force eventually becomes zero, and so the gravitational effect or the gravitational field also becomes small. So this concept of gravity field exists in our imagination from the very moment we were born on this planet. What we are thinking of doing here is to extend the idea to any field, in particular to electric field, and later on in the course to magnetic fields. So to get a proper idea of what a field is, think of the field as a arrow that exists at every point in space, and that arrow size gives you the magnitude of the field. So here, for example, the first row of arrows, the first layer of arrows are all the same size because we are close to the Earth, and then the second layer of arrows are all smaller because we are farther from the Earth. This is an example of gravity field. Now, if we were to put an expression on the gravity field, how would it look like? Well, it would be this acceleration due to gravity at every point on the Earth's surface is the definition of gravitational field, and it's measured in meters per second squared or Newton per kg. I would actually like to fixate on this way of defining the gravity field as newtons per kg because that's more fruitful for the analogy with electric field. So let's look at how we can get this expression for the gravitational field. The starting point would be the Newton's law of gravity. The gravitational force between the Earth and any object, let's say you have an object of mass m, a certain distance from the Earth's surface, from the Earth's center, and let's call that distance little r. The force of gravity is given by Newton's law of gravity, which we studied last week. So that's going to be the gravitational constant of Newton times the mass of the Earth, which I'll call capital M, times the mass of the object, let's say you're an astronaut out in space, divided by r squared. Now, by Newton's second law, this is also equal to mass times acceleration. So that's going to be m times acceleration, and that acceleration is the acceleration due to gravity. If you look at this expression, you find that the mass m, little m, cancels out on both sides, and I end up getting an expression for the gravitational field of the Earth. It is gm over r squared, and if you want to make this a vector expression, all you've got to do is put a vector sign like that. Remember our convention, r hat is the radially outward unit vector. So negative r hat is a way of saying that gravity always points inward and you always tend to fall toward the Earth's surface. So that's the gravitational field of the Earth. Incidentally, you can use this to find the Earth's mass by solving for m. So that's one useful result you get from here. You can find the mass of the Earth by simply measuring the acceleration due to gravity at any location, and the most convenient location for most of us is on the surface of the Earth. So you swing a pendulum or something, and from that you can measure the acceleration due to gravity, and you can put little r equal to the radius of the Earth if you conduct that experiment on Earth's surface, and from this equation you can actually determine the mass of the Earth. So that's a very useful application of the gravitational field. The electric field is exactly like that. You typically have a mysterious situation. So you have, let's say, a charged comb. To take a more complicated example, you take a charged comb and run it through your hair. So that's a badly drawn plastic comb with some missing teeth, and you run it through your hair, and it's going to develop some electrical charge. Now this charge, because there are sharp points here in the comb and some not so sharp areas of the comb, there's going to be a complicated electric field generated by this comb. Now how do you do anything about it? Well, one option is to go to different points. Let's say the charge distribution is given by this total charge Q. It need not be a total charge. It could be a charge that varies from point to point, but I'll just take the total charge to be Q. And then we can take a little charge Q. This is sometimes called a test charge. And the idea behind a test charge is that the charge itself does not distort the field produced by this. It's similar to how if you have an astronaut hovering far above the Earth's surface, the astronaut's gravitational field, even though it exists, will not be such an important factor at all. It won't distort the Earth's gravitational field much. That's the implicit assumption in this particular method. So the test charge is supposed to be a very small charge, which has got some charge so that it can feel the force, the electric force by Coulomb's law. And then at this point, you figure out how much force there is, and then you divide that force by the mass, just as you did here, and you'll find the electric field. So the procedure here is first find the electric force, F sub E, it's a vector, and divide it by the test charge magnitude, and you get the electric field, which is usually indicated by E. The gravitational field is indicated by little g with an arrow. The electric field is indicated by capital E. And you notice that I put the units here of the gravitational field to be newtons per kg, and that is because the units of electric field are very naturally newtons per coulomb. Later on we'll find alternative units for the electric field, but right now this is the most basic definition of the electric field. It is the charge that force that a test charge feels at any given location divided by the magnitude of the test charge. So I'll write here, it's force felt per unit test charge. Now it does not matter that the test charge is positive or negative, because if it's a negative test charge, it will feel an attraction, and you divide by a negative number. If it's a positive test charge, it will feel a repulsion, and then you divide by a positive number. The net effect will always be the same electric field. So in our second week of this course, and maybe a portion of the third week, our main goal will be to try to quantify the electric field, how it's caused and what effects it has. Effects are kind of easier to study than the cause, because to find the effect of the electric field, all you would have to do is put a test charge and see what happens to it. If it moves, then you know, oh, okay, the electric field is something there. So the effect is easy to find. The effect of the electric field is simply got by saying Fe equals Q times the electric field at any location, and that is equal to mass times the acceleration, and from that you can figure out how the test charge is going to behave at any given point. So that's the effect. The causes will occupy the most time. So of course we're not going to consider anything like the comb, it's too complicated. So we'll start by asking simple things. The simplest example of a cause is a point charge. So if you have a point charge like a plus or a minus, how would the electric field look like? So just for the sake of convenience, let's take a positive test charge here. Now a positive test charge, if this has got magnitude q and that has got little q, magnitude little q, then a positive test charge will have an electric field in this direction, because the electric force would be in that direction, and you divide the force magnitude by the test charge magnitude and you'll get a field. So it looks like a positive charge has a field that resembles an anti-gravity field, because all the electric field vectors are pointing away from it. And then because of 1 over r squared, if you go farther out, it'll be smaller. So the next layer of fields will be smaller. Now I've drawn only a few arrows here. You should imagine in your mind that there's an arrow at every point in space. So this is a space filled with arrows. That's the meaning of the field. Now, what about the negative charge? Here, if you put a test charge that's positive, it'll tend to be attracted. So here, the electric field actually mimics the gravity field. So one way to analogize the two fields is that negative charges behave like gravity and positive charges behave like anti-gravity. These analogies are useful for some time, and then later on you'll just stop thinking in terms of gravity and just remove that crutch and just think in terms of electricity alone. So that's the most basic example of the electric field profile. Let's find the expressions for the electric field of a point charge. That's got by Coulomb's law. So the electric field of a point charge, which I'll write E point, it's going to be the Coulomb force, and that's KQQ over R squared times R hat. Okay, this way of writing the electric field per unit charge. So you'll divide this by Q. And that gives me KQ over R squared times R hat. So that's the most basic expression for the point charge. Let's see if it works for positive charges. If Q is positive, KQ over R squared is positive, and that tells you the electric field is in the direction of R hat. Well, that's true because R hat is pointing away from the charge Q. What about negative charges? If Q is negative, this tells us that this quantity is going to be negative and the electric field is going to point in the direction minus R hat, which it does. So this expression, known as the point charge electric field, is the most basic expression for electric fields. It should be compared to the expression we had for the Earth. It's very similar to that. Now, as we study more complicated examples, you'll find some interesting features. I'll just point out two features here. I'll save the details for later. And one is this. The one feature you'll always find is this. If the object occupies a certain dimension, then the power of the field, the power of decay, is going to be the complementary dimension. So for example, that's a point charge, okay? So it's got an entire sphere's worth of freedom. So that's why you get an R squared. Later on, we'll see that if we have a more restricted kind of charge, let's say we have a line charge. So I'll be doing these calculations soon. So if you have a line of charge, that is a very long series of pluses or minuses strung out along a straight line, what kind of field will that produce? It'll turn out to be something like this. E line will be some constant, okay, divided by R times R hat. So you have only one power of R here. And you can almost guess what the answer would be for an infinite plane of charge. I'm going to denote infinite planes by simply omitting the corners. So it means that it extends all the way to infinity. So suppose I have a surface charge. So this would be the analog of taking a large plastic sheet and running it through rollers or newspapers. When they come hot off the presses, newspapers get a certain charge on them, and then this is actually a very big problem, and Kodak had to spend millions of dollars to address the charging of rollers when they come out rapidly. Charging of sheets in from rollers is a huge problem because the ink deposition is affected by it. The electric field of a slab or a plane would be a constant. What about the direction? The direction is going to be whatever direction it's facing. So if this is k hat, it'll be constant times k hat. So that's an astounding result. It means that the electric field never stops being there. So if you go 10 miles from here, the electric field will be the same. If you go a few light years from here, it'll still be the same. Okay? The only difference is if you go a few light years away, you'll see a bigger portion of the slab than you would if you were a few centimeters away, but the effect will be the same. So we'll be looking at all these calculations in more detail